Okay, so we will continue talking about the lecture 4 about convolution, and after that, in the end, we can spend some time to talk about homework 3. If you have any questions. So last time we introduced this very important operation for LTI systems called convolution. So basically, if we feed a signal xt to an LTI system, and if we are given the impulse response signal of this LTI system, let's say it's ht, then the corresponding output generated by the LTI system can be characterized by the convolution between x and h. And this is how we write this convolution notation. And precisely, this convolution is defined as integration of x tau ht minus tau d tau. So here, just to remind you that this t is a given time index that we are looking at. So this yt means the value of y, the value of the output signal at time t, which is the convolutional signal evaluated at time t. So here t is not the variable that we are integrating over in this integration. So in the integration, we are fixing t and integrating over tau. So that is the different. That is the a little bit confusing part sometimes. So we can see that in order to evaluate this convolution, we need to look at this product of signals. One of them is x tau, which is the input signal, and the other one is ht minus tau. Now, if tau is the time index, then this is a reversed and shifted version of the signal h tau. So let's look at a graphical explanation of this convolution example. So here we are looking at the convolution at a particular time t. And for that, we need to calculate this integration. Now let's consider a special case where both the input signal x tau and the impulse response of the linear and time invariant system h tau, both of them are rectangular signals. And in particular, they may have slightly different amplitudes and durations, but the shape is rectangle. So x tau is here is a rectangle signal. We already have that in this integration. So we need to consider ht minus tau. So to generate this signal, we can utilize the basic signal operations. Right? We first do a time reversal from this h tau. We do a time reversal, which generates this h negative tau. And then in order to get ht minus tau, we need to shift. But from h tau, we get h negative tau. This is a time reversal. And then in order to introduce this shift t, we need to do this negative tau minus t. That will give us a positive t in the end. But here, so basically this t will shift the reversed signal, shift this signal to the right by t units. So in the last figure, right, this reverse signal is shifted to the right by t units, and suppose this is the value of t. Now we have this x tau and ht minus tau. So we can do a pointwise product between these two signals. And we know that a rectangle signal multiplied by another rectangle signal pointwise t, that will generate another rectangle signal, and the duration is exactly their overlapping area. So the picture may look like this. We have this x tau signal. And this ht minus taus something like this. Now, once you multiply this rectangle signal together, you end up with another rectangle signal. Well, the duration is basically their overlapping duration. So this, let's say this is t. And the amplitude is the multiplication of the amplitudes of these two rectangles, right? Because everywhere else, one of the rectangle will take 0 values. So that's why their multiplication only corresponds to a smaller rectangle in this overlapping area. So this is h. So this is x tau. This is x tau times ht minus tau, which is basically, you can understand intuitively, you can understand this as their overlapping, kind of their overlapping region. And then we need to evaluate, we need to integrate this product, integrate this signal over time tau, which basically corresponds to the area under this rectangular region. Okay, so this area corresponds to the integration of x tau. And this integration, this area gives us the value of y of t, which is the convolution signal evaluated at t. So basically, to look at the convolution signal at a time t, we need to reverse this h and shift it by t. And then in this case, well, in this rectangular case, the convolutional value corresponds to the overlapping area between these two rectangle signals. And then you can imagine that if we vary the value of t, if we want to look at this output convolution signal at different time index t, then basically we are changing the location, the shifting locations of this h signal. So if t ranges from, for example, -infinity to +infinity, then we are essentially moving this blue rectangle signal from the left-hand side and move it along the horizontal axis to the right-hand side. And once we move this rectangle signal along this horizontal axis, you can imagine that the overlapping area between these two rectangles will change depending on their relative locations. So this will create an animation for visualizing the convolution signal, for visualizing the entire convolution signal. So the first 5 figures illustrates the convolution between x and h at different time t. And the final signal plots the entire convolution signal, yt, over the entire range of t. So we can look at each figure. So the first figure corresponds to the case where this t is pretty negative, such that this. So we are looking at yt at a negative t. In that case, this smaller rectangle ht minus tau is shifted to the left, And then in that case, these two rectangles do not touch with each other. So they have no overlapping area. So in this case, the convolution value is simply 0. So that's why we have flat curve in the negative time domain. And now we keep increasing the value of t. So we're looking at value of we're looking at yt. And we keep increasing this value of t. At some point, they will start to overlap. These two rectangles will start to overlap. So once we increase the value of t, it is equivalent to moving this smaller rectangle to the right. So at some point, these two rectangles will start to overlap with each other. And then that will generate a non-zero convolution value. And we can intuitively, we can see that at the very beginning, once we slide this smaller rectangle into this larger rectangle, their overlapping area, right? As this time shift t increases, this overlapping area will also increases, and at a linear rate. So that's why we have at the very beginning the convolution value is linearly increasing, because this overlapping area starts to increase when we slide this smaller rectangle into the larger one. And then we keep increasing the value of t. So after that, at some point, the entire smaller rectangle signal will be included in the larger rectangle. And in this case, no matter how we move this rectangle inside the larger rectangle, their overlapping area will remain the same. It's the constant, which is the area of the smaller rectangle. So that is why in the convolutional result, right, in this region, the convolution remains the same because they have a constant overlapping area. And then we keep increasing the t. And at some point, the smaller rectangle will start to move out of the larger rectangle. And then their overlapping area will start to decrease, also linearly. So after that, we have a linearly, the convolutional value will linearly reduce until these two rectangles completely detach from each other. So at that moment, the convolution value will simply reduce to 0. Okay. So overall, we can see that if we take convolutions between two rectangle signals, okay, their convolutional result takes a piecewise linear, will give us a piecewise linear function. We start at the beginning, the convolution value starts to increase. This is when these two signals start to convolve with each other. And then the convolution value achieves the maximum value and stays there for a short duration of time. This is when the two signals are completely convolved with each other. And after that, one of the signals is moving out from another one signal. So the convolution there starts to decrease. And then we go back to the 0 convolution. Okay, so in general, convolution is a fixing one of the, when we take convolution between x and h, right, you can imagine that we can fix one of the signals and moving the other signal from left to right. And at each time we take a snapshot, we look at what is their overlapping area. That overlapping area corresponds to convolution value at that moment. So once we move the signal h from left to right, this overlapping area may vary. And this example is just for rectangular signals, which is relatively easy to visualize and understand. But in general, these two x and h, they can be arbitrary and any signals that we discussed in this course. So in general, you have to, like this provides a visualization for understanding the convolution operation. But in general, you have to refer to the mathematical definition to deal with any type of convolution in practice. Okay, so are there any questions regarding this visualization? Okay, and we have shown that convolution is commutative. So basically, X convolution with H equals to H convolution with X. We can exchange their order. So correspondingly, when we visualize these convolution operations, you can choose to fix one of them. You can fix X and move H from left to right, or you can fix H and move X from left to right. So both of these two approaches will produce the same convolution result. Because what matters is their relative position, not the absolute position. Okay, and now we can look at one example, practical example. Let's go back to the definition of convolution. So if I give you that xt is e negative t ut and ht is e negative 2t ut. So given this input signal and the impulse response of the LTI system, now please spend 2 to 3 minutes, work out the resulting output signal yt. So yt would be the convolution between the two. Okay. And please follow this convolutional formula, do the integration, and see what can you get. Okay, so anyone get the results? Do you get the result? 0? Okay, what did you get? Okay, so let's take a look. But intuitively, you can see. Let's think about if 0 is a reasonable answer. So now xt is like is e negative t ut, which is so e negative t is a exponentially decreasing signal, and it multiplied by ut. We have mentioned this. Any signal multiplied by ut, which means we only keep the positive part. So the signal only starts from 0. And same for the ht function. And ht decreases even faster because of the factor of 2. So if we take convolution between these two signals, right? If you think about, I can fix x. I can go back to the convolution. Well, here. I can fix x. Now x is the first figure, and for the h part, I first reverse it, do a reversal, and then do a time shifting, and then move it to the left from left to right. There must be some time when these two signals are overlapping. Right, so think about if I do a time, so this is xt, so this is xt, ht. I'm going to use the same notation here. It's x tau. This is tau, h tau. And if I do a time reversal, this is h negative tau. And then I start to shift this h, reverse the h from left to right. You can imagine that if I start to shift this signal to the right, if I do this one, this is h t minus tau. If t is positive, let's say, and then this red curve will have an overlapping area with this x tau, and at that time they should have a non-zero convolution. So if t is positive, they should have something. Their convolution should be non-zero. But if t is negative, meaning that we shift this signal to the left, then these two curves, they are completely separated. So there's no overlapping between them, and the convolution will be 0. So how do we make this rigorous and do it in a systematic way, following the mathematical formulas? Well, we can follow the first step is to write down a definition of convolution correctly. Now, in the past, many students even make mistakes in the first step. So make sure you write down the correct definition of convolution. It's integration of x tau ht minus tau d tau. And then we are given this xt and ht, so we can substitute these two signals into the convolution formula. So we know xt is given as this one. So x tau is basically, I'm just replacing t by tau in this equation. So that gives me e to the power negative tau u tau. And then the same for the ht minus tau. To get ht minus tau, I'm just replacing t by t minus tau in the h signal. So it's e to the power negative 2 times, I'm replacing t by t minus tau. And u t minus tau d tau. Okay, and then the rest of stuff, we just remember that t is a constant, fixed, given time index. We are integrating the entire thing over tau. So tau is the variable that we are looking at. So because t is a constant, we can pull this out. Try to pull out all the constant ones. So it's e -2t integration e. Here we have e to the power of negative tau, and we have e to the power of -2 times negative tau, which gives positive 2 times tau. And positive 2 times tau minus tau, that gives e to the power of tau. So simplifying and combining all the exponentials, that's e to the power of tau, u tau, u t minus tau, e tau. Okay, just simplifying everything, nothing else. And then we need to evaluate this integration. This t is given. Now, we know how to do integration of exponential functions. But this one, we have this exponential of tau multiplied by 2 unit step functions. And we can very quickly, if you look at the picture of these 2 unit step functions, right? So u tau is the standard unit step function. And ut minus tau, we need to first reverse u tau and then shift it by t. Okay, so it's so this is reversal. And then we shift it by t to the right by t. Suppose t is positive, then we shift it to the right. Okay. So you can see that the product between u tau and the ut minus tau will produce a window function. This is a product of two rectangular-like signals. Right? They are not closed. One side is open. But once you take the product between these two, you can see that one is open to the right, and this one is open to the left. So when you take the product, that is basically, gives us a window function between 0 and t. Because their magnitudes are both 1, so the magnitude remains to be 1. And this is a standard window function between 0 and t. So essentially, so this is u tau times u t minus tau. So you can remember that when you multiply these two unit step signals together, it will create a window function. And because the window function has the amplitude is just 1, so it does not change the function value that we are integrating over. So what it does is to basically restricting the range of this integration, right? Because now we are integrating over the entire time domain, but this product of unit step functions actually gives a window function, and this window function can be understood as restricting the integration between 0 and t, because otherwise the window function basically gives us 0. Therefore, with this observation, we can simply, we can absorb this product of unit step functions into the integration by restricting the range between 0 and t. So it's e tau, e tau. And then we just work out the integration. So this is e negative t. Okay, now remember t is a given number. Tau is the integration variable. So by the integration rule, we have e t minus e. So and this is just 1. So we end up with e negative t minus e negative 2t. So that is the hold on, I think I missed a somehow I missed a negative sign here. E negative t. Yeah, that's correct. That's correct. Okay. So in the end, after integration, the yt. Okay. So this is xt, this is ht. After integration, yt equals to this one. Right, so basically, you just plug in the signals into the convolution expression, and then simplify everything. And you need to realize is that the product of two unit step functions signals will produce. In this case, it will produce a window signal. And after that, you end up with a standard integration over tau. So integrate over tau. The final expression you will obtain is something dependent on t only, and that is reasonable because you are looking at yt, the output signal evaluated at time t. So it's this one. Okay. So this is how you do the homework for. Okay, we have a lot of examples. When you calculate, it's basically integration. You have to work out this integration precisely by plugging all the input signals and the response signals. And in this case, we leverage some special properties of unit step signals to simplify the integration a little bit. And we can also look at the LTI system response to a very standard complex exponential input. This will give us an understanding of some fundamental response properties of the LTI system. So let's say we have a LTI system with the impulse response HT. And then now we are feeding this very special complex exponential signal to the system. It takes the form of e to the power of s times t, where s is any complex number. So S is any complex number. And our input signal is e to the power of st, which is basically e to the power of sigma t times e to the power of j omega t. So this is the standard polar form of the input complex signal. And this is the magnitude, and this is the phase part. The phase is omega t. Right, because the complex unit j is here. Okay, now we feed this complex exponential to the LTS system. Now, what is the output? Very simple. We just follow the convolution rule. We know the output, because it's LTS system. We know the output is given by the convolution between h, the impulse response of the system, and the input signal. And by the convolution formula, we have yt is h tau x t minus tau d tau. Now I'm switching the order between h and x. Because by the commutative law, we can do this. That's equivalent. So I'm looking at h convolution with the input x. So it's h tau xt minus tau. And then xt is e to the power of st. So xt minus tau is e to the power of st minus tau, d tau. So we end up with the second equation. And then because we are integrating over tau, so t is a constant. So we can pull out this constant factor, e to the power of st. So what is left inside the integration is h tau times e negative s tau d tau. And we can see that, so this is the form expression for the output. The output, when we feed this type of input to the LTS system, you can see that the output is exactly the input, right? We have this input signal exactly here as coefficient. It's the input multiplied by some value given by this integration. And if you look at this integration, it only depends on, it is a very fundamental quantity that only relies on the impulse response and the complex frequency that we are looking at S. So we can define this entire integration. We can denote this entire integration as capital HS. So this is kind of like the response of the system given at this specific complex frequency. So to summarize, when we feed this type of input to the LTS system, the output is a scaled version of the input. It's basically the input multiplied by capital HS. And this capital HS, this frequency response is given by the impulse response of the system and the frequency that we are looking at.
I have a question.
Yes.
I'm confused in when you were writing on the right here, where the h of tau and x of t minus tau came from for this example.
So this is because we are looking at, we know this LTS system, right? So the YT is the convolution between H and X, right? And by the definition of convolution, convolution between H and X is defined as this one.
Okay, that's right. Okay, thank you.
In the previous slides, the first time we introduce convolution, we are looking at X convolution with H. So the order between X and H is reversed.
Okay.
Yeah, but we know that the convolution is commutative. So we can exchange the order between these two.
Right. Okay.
But so this is very similar to the linear algebra when we introduced the eigenvalue of a matrix. If you think about the system as kind of a matrix, right? And when we talk about eigenvalue or eigenvectors of a matrix, right? Let me just remind you, right? For any hx m, the eigenvector x is an eigenvector if m times x is some constant lambda times the x, right? So I can view x as a kind of input to this linear system. And so after passing through the linear system, the output, which is mx, is basically a scaled version of the input. Right? If this condition satisfies, then we say that this input x is eigenvector of this associated with this matrix, and lambda is the eigenvalue. Now, if you look at this LTI system, it's exactly the same story. If we feed this type of input signal to the system, the output is a scaled version of the input. So we can say that this type of, I think it's Siri. No, I don't know what happened. Yeah. So when we feed this complex exponential signal to the system, the output is a scaled version of the input. So we can say that this complex exponential signals is an eigen signal of the system. And the corresponding eigenvalue is given by this frequency response. Right, so there's a close relation between the linear algebra and LTI systems. In many cases, you can view a matrix as an LTI system. Okay. So in practice, when we want to characterize the input-output relationship of an LTI system, we need to know the impulse response of the system. So that is to say, when you are given an LTI system, you need to generate an impulse signal and feed it into the system, and then look at output. That will give you the impulse response. However, in practice, the impulse signals are relatively hard to generate because this is an idealized signal. Right? It is not even well defined mathematically, explicitly defined mathematically. So instead, we can do the following. Instead of feeding an impulse signal, we look at the unit step signal. We can input a unit step signal. And this signal can be practically generated because it is simply starts from 0 and then the amplitude is 1. Right? This is a practical signal that we can generate or approximately generated. We feed this type of signal to the system and look at corresponding output. And then the impulse response is basically given by the derivative of the ST. Let's look at this one. But if you feed UT to the system, LTI system H, and look at output ST. Now because it is LTI, so we know ST is given by U convolution with H. Okay. Now we look at the derivative of ST. Which is basically the derivative of this convolution. And by the differential property of the convolution, we have one slide for that. Here's the differential property. The derivative of a convolution signal, we can instead take in the derivative of any one of them first, and then take the convolution. So in this case, I can look at dut dt first. I choose to look at this one first, and then take convolution as ht. And we know that the derivative of unit step functions is the impulse response. Right, the derivative of unit step is the impulse response, and any signal convolution with the impulse signal is the signal itself. So this proves that the derivative of this output is exactly what you want. It's the impulse response of the system. So this is how you can practically measure the impulse response of this system. So instead of looking at generating a idealized impulse signal, you can just feed a unit step signal to the system. And then on the output side, you look at its derivative. The derivative gives you the impulse response. Right? And this only works for LTI systems, right? Because here we are leveraging the properties of convolution. And the rest of the slides we are basically regenerating all the concepts for discrete time LTI systems. And the story is exactly the same. So we can quickly go over this. For example, in the continuous time, we introduced this impulse signal. So in the discrete time, we can also define the discrete time impulse signal. And in this case, because everything is discrete, so this discrete time impulse signal can be explicitly defined, and it is very intuitive. Basically, at this discrete index 0, it takes value 1, and everywhere else it takes 0 value. Okay, so in this case, it is explicitly defined. And we can also, this is a time shifted version of this discrete impulse. So it's very natural. And then following in the continuous time, remember in the continuous time case, we can represent any signal by this. We have this general representation of any signal in terms of the impulse signals. Similarly, for discrete time, we also have the same expression. So we basically changing integration into summation, and everything else is the same. So this is basically to decompose a discrete time signal by a bunch of weighted and shifted discrete impulse signals. And the picture, if I draw any discrete time signal, right? This summation exactly gives so for every of this discrete time, for example, for the signal here, I can shift a discrete time impulse signal to this location and then scale it corresponding using the corresponding value of discrete time signal. And then I sum up all these discrete impulses that will essentially give me the discrete time signal itself. Okay, and again, for discrete time systems, we can also define the LTI system. It is linear, it is time invariant. Right? When we introduce the linear and time invariance, these two concepts can be applied to both discrete time and continuous time systems without loss of generality. So again, we can show that following the same proof, we can show that the output of the discrete time system is given by the discrete convolution between the input and the impulse response. So first of all, we define the impulse response in the same way. We feed the impulse, discrete time impulse, to the discrete time system, and the corresponding output is the impulse response. And then the input and output relation for this discrete time LTI system is given by a discrete convolution. So the convolution, discrete convolution between X and H is given in this way. If you compare this with the continuous time convolution, if you look at this one, they are exactly the same except for a change of notation, right? We are summing over K. Here we're integrating over tau. Here we have xk Hn minus K. Here we have x tau Ht minus tau. Exactly the same. And the corresponding underlying visualization or intuitive explanation are also the same as what we have shown in the continuous time convolution part. So we are fixing one of the signals X, flip the other one H, and move it from left to right. And because it is discrete, so when we calculate this convolution, we have to calculate these summations. And calculating summations are fundamentally different from calculating integrations. So in some sense, doing integration is simpler because we have those nice formulas. But calculating summations, we have to, in most cases, we have to deal with a lot of terms and sum them up. So there's no simpler way to deal with this one. So this is how we calculate the convolution between two discrete time signals by hand. And we can look at this. So we have this xn and hn. And xn takes non-zero values between 0 and 7. So we have x0 and x up to x7. And for the h, this signal only has non-zero values between 0 and 3. Okay, so these are just two discrete time signals given by two vectors. And then mathematically, we need to follow this formula to calculate the convolutional signal. However, we can use a matrix multiply method to do this in a matrix vector way. So this is how we do this. We know that convolution is basically fixing one of them and moving the other one. So in this case, in this example, I'm gonna fix H, but you can also fix X. It's the same idea, basically exactly the same idea. So let's fix H. When we fixing this H, we are basically writing this H signal, listing this H signal as a column vector, one by one. We have 4 elements, so it's a column vector here. Now H is fixed, and now we are going to move this X signal. So we are going to generate this big matrix that simulates the movement of the X signal. So this is how we explicitly simulate the movement. We start with this X signal. We will list it as a column vector in the first column. And then we start to shift this column vector downwards one by one. So you can see that in the second column, the entire X signal is shifted downwards by 1. And in the third column, we further shift it by 1. We do this column by column. Now, how many columns do we need to generate? You just need to look at the dimensionality between the matrix and the vector. So because we have because for the H signal it has 4 elements, so the dimension is 4. In order to have a compatible matrix vector multiplication, for this big matrix, you need to have 4 columns, right? Because you need to have 4 columns. Then you can have a compatible matrix vector multiplication. So basically, the dimension of H determines how many shifts you need to do for this X signal in the columns. So because we have 4 elements in the H, so we're going to generate 4 H signals, 4 X signals, and they are shifted one by one downwards. Now, once you create this big matrix and fixing this H vector, all you need to do is to follow the matrix vector multiplication rule, and you will end up with the corresponding outputs of the discrete convolution. And you can actually verify, because Y0, if you look at the first element, is basically the first row times this column, which is basically X0 times H0. This is the first time when the signal when the signal X touches the signal H. And then you take if you look at second one, you start to have X1 and X0s moved inside. So the second row multiplied by this one, you have X0 H1 plus X1 H0. So it's like you are moving the X signal towards the H signal. And once you go further, you have more elements to appear in the X signal. So it is like the X signal is moving to the right-hand side. So if you look at this row by row, you can see that visually you can see that all the elements of X signal, they start to move to the right-hand side. And then in the fourth row, the X0 is out of range, so it disappears. And instead, we have X4 moving in. So in the end, in the last several rows, right, the X signal is moving out of the range of the H signal. So basically means they are starting to moving away from each other. So this exactly simulates the entire discrete convolution process. And you can see that the X signal in each row, it is reversed, right? Because in the convolution, we need to reverse the X part, and before we shift it. So this is exactly illustrates how we do discrete convolution. Okay. So if I give you 2 discrete signals, you should be able to follow this matrix multiply method to do this discrete convolution. And in general, we can, for other cases, we can also work out the discrete convolution by following the original mathematical formulas. For example, here we're looking at an input signal, which is a unit discrete time unit step signal, UN. And for the discrete LTS system, the impulse response is given by such a discrete time signal, 1/8 to the power of n times UN. Okay, so we need to calculate the corresponding output for the LTS system. That is basically given by the discrete convolution between these two. And again, we just follow the formulas of discrete convolution, plug in everything, and then do the summation. So by definition, the discrete convolution is defined as follows, right? This is just definition. And then we can substitute X and H inside. So for the HK part, we just replace here, we just replace small n by small k. So we have this part. And for the x part, it is n minus k. So we need to replace n here by n minus k. So that gives us u evaluated at n minus k. Okay. So plug in this x and h, we get this summation. Again, you see we have a product of two unit step signals. So following a similar observation as we did in the continuous time part, this product of two unit step signals essentially corresponds to a window, a discrete time window signal. And that window is between 0 and n. Between 0 and n, we can verify that. So basically, we can absorb this product of two unit steps signals into the summation by restricting the range of the summation to be within 0 to n only. So now we are looking at summation between 0 and n over 1 over 8 to the power of k. And this is a standard finite summation over finite number of geometrically decreasing terms. So we have a formula for that. Here's the formula. Geometric series summation formula. So you apply this formula, you end up with this result. And in the exam, I will provide this formula. So you just need to plug in the parameters corresponding. But if you follow this formula, so this R is 1 over 8. Capital N is small n. Capital M is 0. So according to the formula, the first term we have is R to the power of M, which is 1 over 8 to the power of 0. That gives us 1. Anything to the power of 0 is 1. Okay. And similarly, for the other terms, you can work them out. So in the end, you end up with this signal, discrete time signal. So you can see that most likely, if you want to calculate discrete convolutions, you have to deal with, in many cases, a finite or even infinite summation series. And that's where you need to utilize this summation formula for the geometric series. And for discrete convolution, we have exactly the same properties as what we have for the continuous convolution. Commutative, associative, distributive, everything is the same. And we also have this very fundamental properties. Any discrete signal convolution with the impulse, discrete impulse, is the signal itself. And also, remember in the continuous time convolution, we have this delay property. If two signals, they are delayed respectively by tau 1 and tau 2, then after convolution, that will generate a delayed signal y with delay tau 1 plus tau 2. So the delay for both parts will be add up. So this is a very special property that we are going to leverage when we deal with Fourier transform. Okay, and the other stories are the same. For example, when we talk about LTI, continuous time LTI systems, we have mentioned that we can look at the impulse response to categorize the LTI system. Here's the same story. We can also look at the discrete impulse response of the discrete time system to categorize all the system level properties. So here I will not repeat all those applications. So you can refer to the continuous time part. It's exactly the same. And this ends this lecture 4, where we talk about LTI systems and the convolution. So from this lecture, we realized that for this fundamental LTI system, first of all, it has many applications that we discussed in circuit systems, and especially that can be represented by differential equations. For these LTI systems, they can represent it as the convolution of the input with an impulse response. So that's a very nice property. We just need to know the impulse response of the system. And the convolution is a very basic operator that has many properties similar to the multiplication in the number system. And we have shown that how to leverage this impulse response to understand the fundamental properties of LTI systems, like stability, causality, invertibility, and so on. And we have worked with many examples to see how to do the convolution by hand for continuous time and discrete time convolutions. Okay. And to motivate the next lecture, which we will start after the midterm, right? One observation is that while convolution is conceptually simple, we derived it following the linearity and time invariance of the system. However, it can be practically difficult and tedious to convolve, especially when you have to work out those integrations following the convolution formula or the summations following the discrete convolution formula. So there has to be a better way to deal with this convolution in the LTI systems. So that's why in the lecture 5, we start to introduce the Fourier transform to better deal with these convolution operations. Okay, so I think that's all for the lecture 4. So any questions for this? If there's no questions, we can quickly turn to the homework 3 and see if you have any questions for this one. Okay, which one?
So 2 on like any of them, how to figure out if it's stable or not? Do you go over that?
Are you talking about all of them or?
Just like the strategy, because I can
Okay.
only like remember how to figure out if it's stable or not.
Yeah. For example, we look at the last one. We can look at the last one, and we can check the stability of this system. Now, stability means that if xt, if the input signal is universally bounded by a constant m, I mean the magnitude, to be precise, the magnitude of the input complex signal is bounded by constant m for all t. Then we need to show that yt is also universally bounded by another constant m prime. So we can look at the yt. So the goal is to bound the magnitude of yt. So we can look at the magnitude of yt. And the system equation says that yt is the input xt times cosine 3t. So basically, we need to bound the magnitude of this one. And we know that the magnitude of xt is bounded. So first of all, the magnitude of a product of two complex numbers, we know that it is the magnitude is the product of the individual magnitudes. A basic property of complex numbers. And then you can start to think about whether or not this magnitude of yt is bounded. Because we know that, first of all, this one is bounded by m, is given by the condition. So we can say that it's bounded by m times cosine yt. The question is this part universally bounded by a constant? Right, it's a cosine signal, so we know the amplitude for cosine is at most 1, so we can conclude that this is bounded by m. Right, so that shows that if the input is bounded by m, output is also bounded by m, which means it's stable. So that is the proof logic for verifying the stability of system. Yeah. So other questions? Have you guys worked out the last one? I think it's in the book that this one. Interconnection of 3 systems. So do you have any question on this one, or should I? We have about 7 minutes. So in the end, the input, the overall input and output relationship should be a very simple formula. Did you get a very simple one?
Not really. Could it still be
Piecewise? Okay. We can. Not sure if I have time to finish this one. Let's see. After system 1 is piecewise, system 2 is piecewise, but after system 3, you should get rid of the piecewise thing here. So okay, let's work it out here. So I'm gonna put xn inside system 1. So the output, I call the output of system 1 is y1n. According to the system equation, is x n over 2 if n is even and 0 is odd. Okay, so this is the output of the first system. Now we're going to feed this into the second system. So on the output side of the second system, looking at y2n, I call it y2n. And by the second system equation, the output is given by input in this way. But now the input is y1n, so we need to replace x by y1. So according to the system equation, it's y1n plus 1/2 y1 n minus 1 plus 1/4 y1 n minus 2. Okay, and then because y1n is we have 2 cases for y1n depending on the evenness or oddness of the input of the index n. So we also need to discuss the evenness and oddness here. Now, if n is even, if n is even, then y1n should use the first formula, which is x n over 2. And if n is even, n minus 1 should be odd, right? So y1 n minus 1 should follow in the second formula, which is 0. So this one is 0. Moreover, if n is even, n minus 2 is also even. So n minus 2 follows the first one, which is the. Now I'm going to replace n by n minus 2. So that gives me, okay, a little bit careful here. Right, so that's the even. And odd part, you do the same thing. I will skip this one. So if n is odd, you for the first term you follow the second one. For the second term you follow the first one, and for the last one you follow the second one. Okay, a little bit confusing, but in the end, okay, this is only after the second system, and in the last system, right, y3n is actually now the input is y2, is the output of y2. So y3n is y2 2n. Okay. And because y2 is also following y2 also depends on the evenness and oddness of the input. But the tricky thing is that now the input to y2 is always an even number, no matter n is even or odd. There's no even number times 2 is even, odd number times 2 is even. So 2n is always an even number. So the input to y2 is an even number. So you need to follow the first formula to get y3n. So that's why in the end, we don't have that piecewise linear stuff. Okay, so this is I guess you have to go over this very carefully to figure out the final equation. Yeah.
Question on that one for the 1/4x and a -2. Your even part there. Where you have evens. You're replacing n with n/2, right?
So if n is even, right, n minus 2 is even, right? It's an even number minus 2 is an even number. So,
Okay.
so in this case, when n is even, the input to this y1 is an even number. So then the input is even, so you need to go back to the formula for y1. So when the input is n is even, you're going to use the first formula. Right? And then you are going to replace n by n minus 2. That is y1 n minus 2. That's why we have x n minus 2 over 2 here.
Oh, we're replacing
So,
n with n-2.
yeah,
Okay.
this gives the relation between the input to the entire system and the output of the y2, the system 2, right? When the time index n is even. Yeah, and when the time index n is odd, you need to go back to these three terms again and check their evenness and oddness of their inputs. And then further go back to y1 to figure out how they depend on the real input, the underlying input to the system. Okay. So, okay, if you have other questions, please talk to me in the Zoom. I will be there for the office hours in my personal Zoom link. Okay, I will see you guys then. Yeah, see you then.